I'm Thomas Barnard, and this is a report on the work of Linus Pauling and Matthias Rath on heart disease. They called their theory a unified theory of cardiovascular disease. I mean, unified theory, that sounds like Einstein, but okay. It's still a brilliant theory. So I have previously reported on the work of Dr. Christopher Willis, who wrote 5 or 6 papers between 1952 and 1957 on atherosclerosis and vitamin C. He found a remarkable thing. Using guinea pigs. Guinea pigs mimic the cardiovascular setup of humans in that guinea pigs don't make vitamin C, humans don't make vitamin C. And guinea pigs have plaque, and so do humans. So what he found was, briefly, that if he didn't give the guinea pigs vitamin C, they would develop plaques. And if he did give them vitamin C, the plaques would go away in one experiment completely. Now, he did a small preliminary experiment with humans, and plaques became smaller. I mean, maybe it's a matter of amount of vitamin C or length of time, and he would get the same results, or he certainly thought he would get the same results in humans. So this is kind of a starting place for Linus Pauling and Matthias Rath. His paper, Willis's paper, was called The Reversibility of Atherosclerosis, which is a remarkable title. So maybe Willis didn't understand the mechanism of action, but maybe it's not important after all. Penicillin was discovered in 1928, and it wasn't until, the mid-1970s that they discovered the mechanism of action in penicillin. Nevertheless, it saved a lot of lives during World War II, and so that's why I say it may not be so important. Maybe it's the only thing that's important to know about heart disease is that lack of vitamin C's will cause the plaques, and vitamin C administration will eliminate the plaques. But there is more to know. And Pauling and Rath added to our knowledge, and maybe added also to the solution. One of the important things of their work was that Rath found in the plaque the compound lipoprotein A, also called LPA, LP small a. And that seems to be the crux of their findings. They thought it was a repair molecule for collagen that was broken. And in fact, they wrote a paper called lipoprotein A is a surrogate for vitamin C. Now, Rath was focused in on that end of it, but Pauling comes with a unique experience about chemical bonding, which comes in handy. And where did that chemical bonding knowledge come from? Well, he went to Germany in the 1920s. He was there in the mid-20s when all the exciting quantum mechanics work was being done. He studied with Sommerfeld, Niels Bohr, Erwin Schrödinger, all of these key people in the quantum mechanics theory. What happened is that he took this knowledge back with him to Caltech, and he could use quantum mechanics to figure out how far away these atoms were from each other in a molecule, and so he was able to figure out the structure of some of these molecules. So his work coalesced in a text called The Nature of the Chemical Bond. And it was for that and maybe some other things that he won the Nobel Prize in chemistry. And after that, he found arguments against war, and I think that culminated in the test ban treaty in the early 60s, and he won a Nobel Prize for Peace. And he might have won a Nobel Prize for the structure of DNA. If you see the TED Talk that Jim Watson gives, he plainly wanted to study with Linus Pauling, who he thought was, the great genius of chemistry. And he applied to Caltech, but Caltech, in its infinite wisdom, turned him down. He goes to Indiana University, which was probably more advanced in this heredity molecule that he was focused in on. He goes eventually to Cambridge and teams up with Francis Crick, and they almost literally steal a look at Rosalind Franklin's DNA X-ray photography, which told them that it was a helix, that they were needing to figure out the structure. Is a big hint. Linus Pauling wrote for those pictures, but they never came to him. And he wasn't able to travel. It was the McCarthy era, and in the early 1950s, he had trouble with his passport. So he missed out on that one. But, I mean, he did this work on heart disease. I think it's pretty important. So, where Willis found where the plaque was, with the mechanical stress of the heart, with the turbulence when a large blood vessel bifurcates into smaller vessels, he's able to explain that what happens there is that blood vessels, the collagen in blood vessels is breaking apart, and without sufficient vitamin C, now vitamin C's role in the manufacture of collagen wasn't outlined until maybe 1962. So Willis, when he was writing in 1957 and the early 50s, he didn't know about that. But Pauling and Rath do know about it, and that's part of their theory, that when the collagen breaks apart from this mechanical stress, proline and lysine may stick out, and this molecule, lipoprotein A, will bond with those amino acids, and then you get the whole cascade of events that make up the plaque, the LDL, the fibrogen, the fibrinogen, the plasminogen, the foam cells, the calcium, the whole smear. And it's because LPA binds with lysine and proline that Pauling and Rath recommended taking free lysine and proline to bind with the LPA and prevent it from repairing the collagen. I mean, it's this repair thing that's causing the whole problem. But you get a twofer if you take lysine or proline. These are components of collagen, and so should aid in the production of that collagen. So that's important. So not long before Pauling and Rath begin their work in the late 80s, science seemed to make a wrong turn. It focused in on LDL. LDL, as we all know from TV commercials, is the bad cholesterol. And a mania begins with the November 1984 publishing in Scientific American of an article by Brown and Goldstein. Brown and Goldstein were researchers in Texas, and they won Nobel Prizes for figuring out a mechanism that LDL might use to bind with blood vessels. Now, it turns out that LDL is a transport molecule. It has a function. Its function isn't to cause heart disease. Its function is to ferry about 1,500 molecules of cholesterol out to the cells from the liver. And but it does seem to be a wrong term, and this seems to be highlighted in an article by Robert DeBroef in the American Journal of Medicine, where he says there should be a reappraisal of the lipid hypothesis. Basically, he looked at 29 big studies of these cholesterol-reducing drugs, the statins, and he finds that in these 29 studies, only 2 of them have any kind of mortality benefit. And if there's no mortality benefit, why are we so interested? So he was also concerned about confirmation bias, which is scientists trying to make the studies work and show what they're trying to show. And he was concerned about conflicts of interest because the cardiologists who presented these results in seminars to attract other doctors to these drugs were well compensated. So, interestingly, it turns out that LDL plus an ApoA molecule makes LPA. So it's a small world, LDL, ApoA, lipoprotein A, and that's what. But it's the ApoA that binds to the proline or lysine, and their theory is that LPA is this repair molecule, and it's created to to close the micro gaps in blood vessels that occur with the stress and so on. Interestingly enough, you would think that if LDL went down with these drugs that LPA would also go down. Not so. Apparently LPA has this special function because LPA can go up even though LDL might be going down. Vitamin C is essential in the manufacture of collagen. Most of the animals in the animal kingdom make their own vitamin C in the liver. And they don't have the problem that humans have, who maybe 40 million years ago lost the ability to make vitamin C. So, Pauling and Rath think that heart disease is really a vitamin C collagen deficiency disease. I mean, if you're deficient of vitamin C, you're going to be deficient of collagen. So, collagen is just critical. Linus Pauling calls collagen the principal structural macromolecule in animals. In plants, that would be accomplished by cellulose. They've discovered some 28 different types of collagen so far, and but all of them seem to have the amino acids lysine and proline and vitamin C is necessary to hydroxylate them and thus incorporate them into incorporate them into a collagen molecule. I asked a couple of AI search engines, and some gave me no answer, but two of them told me that I wanted to know how many molecules of ascorbic acid of vitamin C are necessary for the manufacture of a molecule of collagen, and the answer came back 300 to 400 molecules of ascorbic acid are necessary for a single molecule of collagen. So this is a pretty important molecule. Pauling knew about collagen because he knew about scurvy, and that's what they called this vitamin C collagen deficiency disease, scurvy. And maybe 300 years ago, you would find sailors at sea for months, and they wouldn't have sufficient fresh vegetables or fruit on board, and they would come down with a group of symptoms they called scurvy. Those symptoms: bleeding gums. You might get black and blue marks that don't heal. A tooth might fall out, or a couple of teeth. And then finally what happens is your blood vessels fall apart and you die from internal bleeding. Either that or infection, and Linus Pauling dealt with that in other books that he wrote, beginning with Vitamin C and the Common Cold. Thinking about these collagen deficiencies, and this is just on my own, I just wondered if, like for example, there are an awful lot, when you get to age 60, you notice an awful lot of people are having knee replacements and hip replacements. And, it occurred to me, well, what's in a knee? Meniscus, cartilage, ligaments, tendons, bones, muscles. These are all made of collagen. And if you're getting insufficient collagen for years or decades maybe, you might be 6 decades old and having insufficient vitamin C all of that time, your knees might, the collagen in your knees might look pretty scrawny. And so, that might cause arthritis, and maybe then you have to, get a knee replacement. Your ortho guy will give you pain medication, and when the pain medication doesn't work, then he gets to do his thing. You might try a sports medicine guy. Sports medicine guys do different things, and they know, most of them know about vitamin C, and most of them know about collagen. Most of them are familiar with the stem cell stuff. So I'm not placing a commercial for them, but I'm just saying. I've never seen any brain studies, but it seems to me if the blood vessels going to your brain are clogged with this repair combination, the lipoprotein A, the anchor molecule, the lipoprotein A, and the whole entourage of fibrinogen and plasminogen and foam cells and calcium, that you might not be getting that much oxygen to your brain. And I'm just speculating. I'm way out on a limb, but you might want to think about that. All right, there is an important question to think about, and that's how much to take. And let's think about how Pauling came to his recommendation for vitamin C strength. The recommendation of Pauling and Rath is 3,000 milligrams of vitamin C and maybe 2,000 grams of lysine. And he thought the thing to look at is what is the vitamin C production in animals who make their own. And I don't know that there's been enough work done on this, and there's a lot of variance, because I've heard that goats make 13 grams of vitamin C a day. That's quite a bit. But there's a common number that for dogs, you can find this on a search if you look. They make about 18 milligrams of vitamin C per pound per day. So if it's a 100-pound animal, that would be 1,800 milligrams a day. And if it was a 200-pound animal, that would be 3,600 milligrams, or 3.6 grams. And so their 3-gram recommendation is kind of in there. Although, two things. One is that if a dog is under stress, it'll make double or triple or quadruple or whatever times the amount of vitamin C it would normally make. Speaking of Linus Pauling, he says in his lecture at Stanford about heart disease and vitamin C that he started taking 3 grams a day, and then he worked up to 10 grams a day. And when he was taking 10 grams a day, he collected his urine to see how much was passing through. He found 1.5 grams out of 10 grams. That means that he was using 8.5 grams a day. So that 3 grams might not be sufficient for him. And I think that this would be a good thing to do an experiment on, to get some sense of what that saturation point is, because that might be useful to know. We know what deficient vitamin C can do. It can give you heart disease, and maybe it also gives you lousy knees. So I think you could design an experiment and collect the urine and find out, give somebody 3 grams, 4 grams, 5 grams, whatever, see what passes through. This would be important knowledge to have. What did Christopher Willis give his guinea pigs who were able to vanquish atherosclerosis? And it's just, he doesn't really say. He says he starts them out with an intraperitoneal injection of 75 milligrams, and then says he liberally adds ascorbic acid to their chow. I don't know how you would interpret that, but for me, that's not very useful. But we know that, that in 42 days of this diet with the vitamin C, that they'll be without atherosclerosis. He gave to humans, he gave them 500 3 times a day because it's water soluble and it leaves your body when you urinate. So 1,500 milligrams, and he uses periods of time from 2 months to 6 months to look at the arteries. And so I mean it's a preliminary study. It's not a beautiful study, and but 6 out of 10 experimental subjects saw their plaques get smaller. So this backs up the guinea pig study. Now, in a good theory, things come together, and they say that primates lost the ability to make vitamin C 40 million years ago. So on my own recognizance, I wondered, when did this LPA come along, which is supposedly a repair molecule, according to Pauling and Rath. And my searches turned up 40 million years. These things come together. We lost the ability to make vitamin C, and we get the ability to make this other molecule right around the same time. I mean, what are the chances? So on the downside of the vitamin C thing, if you take a lot, you may develop gas. If you take an awful lot, you'll get the runs. And but on the other hand, Linus Pauling and this Gifford Jones, Dr. Gifford Jones, that I'm going to mention in a minute here, think that it has a nice laxative effect. So if you can figure that out. So kidney stones look like they're a problem for men, not so much for women. And I'm wondering about what's causing that problem. You would think the chemistry for men and women with respect to vitamin C would be pretty much the same. I don't think you'll get any, I don't think men will get any vitamin C or have any kidney stone problem if they get their vitamin C from food, which is to say, if you're eating fruits and leaves and so on, probably no problem. But you're also getting some hydration with those things. And these kidney people always say the big problem is hydration. So I'm wondering about if men hydrate as well as women, for example, and maybe there could be some experiment to find out about that. It's a controversial subject, and certainly if you get kidney stones, I mean, vitamin C is pretty much known to create oxalate, but how come the oxalate doesn't result in stones in women but does in men? I mean, there's something to know there. All right, I'll finish up try to finish up on a positive note. I've got two anecdotes and two anecdotal stories and an idea. So the two anecdotal stories, well, one of them would be Linus Pauling. He started taking vitamin C in his 60s. He was taking 3 grams, and he got up to 10 grams, 12 grams. I don't know really where he finished up, but he was taking quite a bit of vitamin C. And so, he died at 93, and he didn't die of heart disease. He died of something else, I think prostate. So, I mean, that's pretty good result. Pretty good. Speaks well for his theory of heart disease. And I have the anecdote of the guy who interviewed Linus Pauling, and that would be Dr. Gifford Jones, who was a medical journalist for the Toronto Star for some decades. He had to assume the pseudonym Gifford Jones because medical societies in Toronto thought he was trying to steal patients away through his column. And his real name was Ken Walker. He was a graduate of Harvard Medical School. In fact, he was the only Canadian at Harvard Medical School the year he went. And so he wrote a medical column, as I said, for decades, and he interviewed Linus Pauling twice when he passed through Toronto. And, he was really impressed. Thought he was a genius and so on. And to be sure, Linus Pauling was one of the greatest scientists of all time. He's right up there. So he interviewed Linus Pauling, learned about vitamin C, although not particularly in relation to heart at that time. But he went home and changed nothing. So 15 years later, as he tells the story, he had a massive heart attack, and that was followed by a triple bypass. And after all that was done, his doctors came to him and wanted him to take, his cardiologist wanted him to take cholesterol-lowering drugs. But he's a doctor, and he didn't like the side effects of those drugs, and so he didn't want to take them, and that's where he parted company from his cardiologist. He had followed the work of Linus Pauling, and now with Matthias Rath, and that they had developed a theory about heart disease. And he knew their recommendation of 3 grams of vitamin C a day and 2 grams of lysine, and he made his own determination, and he took 10 grams of vitamin C and 5 grams of lysine a day. And he just died recently at 101. So I consider that a really successful recovery from his triple bypass and heart attack. So finally I have an idea, and the AI engines say it's possible. So what we know is that we have all the equipment to make vitamin C. I mean, you start here with glucose. There are 10 different steps, ending with the gulo enzyme, which is the last step, and then you get over here vitamin C. We don't make the gulo enzyme anymore. So we have a gene that doesn't quite work. It's called a pseudogene. And the AI engines say that maybe with CRISPR or something we might be able to turn that last one back on. And that would solve the problem for all of us. You might, I mean, there are plenty of primates in the animal kingdom that don't make vitamin C, so you got lots of test subjects. You could see if the feedback mechanism is working. You can, you can maybe solve that problem. Might not be any money in it for a pharmaceutical company, but there'll be a Nobel Prize in it for somebody. So hopefully somebody will take up the challenge and help us all. And that would be just great. So thanks for listening.